This is video 12. We start a new section dedicated to a two-dimensional toolbox. In the following videos, we do not consider tile assembly system but paths and graphs. The lemmas developed here will be useful to prove the macroscopic lemmas. Consider a simple B-infinite path W. This path is called a window and is represented in gray. Windows will be used to cut the grid in two parts. Here we consider a simple example where the window is in horizontal line which goes from the west to the east. The hashed zone represents the left side of the window. And here the hashed zone represents the right side of the window. In this case, it is easy to define the left and right side of the window. The two classical ways to disconnect a graph are cuts and vertex separators. A cut disconnects the graph by removing edges. In our study, we prefer to consider positions of the grid, then we need another approach. The second classical approach is the vertex separator. A vertex separator disconnects the graph by removing positions. Let's remove the position of the window in our example. Here we obtain two graphs which are the left side and right side of the window. In this simple example, the vertex separator is a good approach. Now consider a more complex example. Here another window W. Let's remove the position of W. Here we disconnect the graph into 5 connected components, whereas we want to obtain only 2 components. Then we need another approach. Let's look at our window W. We start by defining locally the left and right side of W. Consider the following positions of W at index I1, I2 and I3. Let's zoom on the position of W at index I1. The position of W at index I1 is the extremity of 4 different edges. Remark that 2 of them belongs to the edges of W. These edges are not interesting. Consider the 2 other ones. They do not belong to the edges of the window. Locally the direction of the window is from the south to the north. Then consider the position of W at index I1. The edge on its west side is strictly on the left side of the window. This edge is in red. The other edge is strictly on the right side of the window. This edge is in blue. Let's zoom out. Now we will consider the position of W at index I2. In this case, locally the window W goes from the south to the east. In this case, the 2 edges are strictly on the left side of the window. They are both in red. This position of W is called a corner. Let's zoom out. Now we consider the position of W at index I3 which is also a corner of W. In this case, locally the window W goes from the north to the east. In this case, the 2 edges are strictly on the right side of the window. They are both in blue. Let's zoom out. In fact, up to rotations, all the different cases are similar to the 3 previous ones. Let's represent all the edges which are strictly on the left side and strictly on the right side of W. The red edges are a cut and the blue edges are also a cut. Before defining our cut of the grid, we have 2 remarks. First, the definition of the right side and the left side is made locally. Thus it's possible to extend this definition for any position of a finite path except for its first and last position. Secondly, if we switch the direction of the window then the red edges become blue and the blue edges become red. The left side and the right side are switched. Now we define a cut of the grid. A cut of grid is a couple of 2 graphs G1 and G2. Here we represent the graph G1 which is the left side of the cut of the grid. This graph contains all the red edges but no blue edges. This graph is also the connected component of the cut made by the blue edges which contains the window W. In particular, remark that this blue edge does not belong to the graph G1 even if both of its extremities belong to G1. Here we represent the graph G2 which is the right side of the cut of the grid. This graph contains all the blue edges but no red edges. This graph is also the connected component of the cut made by the red edges which contains the window W. In particular, remark that these 2 red edges do not belong to the graph G2 even if both of their extremities belong to G2. Intuitively, G1 and G2 are such that their union is the grid graph and their intersection is the window W. We claim that for any window W, it is possible to find G1 and G2 such that these constraints are satisfied. We will not prove this result, but in the following video, we show all the different kinds of window considered in this article. In each of these cases, it is easy to prove that a cut of the grid can be found for any of these windows. Before finishing this video, we present the different kinds of positions and edges. There exists three kinds of positions. In this example, the position U1 belongs exclusively to the graph G1. The position U2 belongs to the window and then to both graphs G1 and G2. The position U3 belongs exclusively to G2. Remark that at any path from U1 to U2 has to intersect with the window W. This remark will be used frequently along the end of the proof. There exists 5 kinds of edge. The edge E1 belongs to the window and then it belongs to both G1 and G2. The edge E2 has at least one of its extremity which belongs exclusively to G1, then this edge belongs exclusively to G1. Similarly, the edge E3 belongs exclusively to G2. Both extremities of the edge E4 are in the window but it belongs exclusively to G1. Similarly, both extremities of the edge E5 are in the window but it belongs exclusively to G2. Here is an important remark. Consider a path P. If all the edges of P belongs to G1 then P is a subgraph of G1, but if all the positions of P belongs to G1 then P is not necessarily a subgraph of G1.